what about second order differential equations? So here's my example. Can we apply the Euler step method to generate a numerical solution to this without relying on the analytical solution at all, just using the information contained in the differential equation of the initial conditions? Can we do that and get something like the analytical solution? So here's my second order differential equation as an example with some initial conditions, which we need 2 of them now. Here's how I got the theoretical solution. I think we've done this exact example before. That's why I chose it. So you guess x equals e to the lambda t, you get a characteristic polynomial, you get some roots, they're complex, you get a complex solution, you use the real and imaginary parts to generate yourself a general real solution, you impose the initial conditions, and you get some values for the coefficients c1 and c2, then you get yourself a particular solution, which I have plotted here. So here's my particular solution, and here's a plot of it from t equals 0 to t equals 10. This is all like part of my theoretical analysis. This is my sort of theoretical solution. Now I want to use the Euler method idea to step little by little in time, do no solving, but just generate a numerical solution and hope that it looks similar to this and maybe has similar features to other numerical solutions where shrinking the time step for the approximation gives me a better and better approximation. Okay, so the way to think about how to do this is still in terms of a table, but there's just another column, that's all. So we have our different times, starting at time 0 here, where we have to choose a time step. So let's choose delta t equals 0.1 or something like that. So the times go 0, 0.1, 0.2, etc. Let's put in one more, etc. Then we've got our different values of x, which we know the first one is 1. Then we've got our different values of x prime, which we know the first one, this time due to an initial condition. We know x prime at time 0. That's one of our initial conditions now, 2. And that is, hopefully this is actually sort of, hopefully doing this will help you see perhaps even more clearly why 2 initial conditions are needed for a second order differential equation. Then we've got our x prime primes, which we're not given this one as an initial condition, but look, this tells you x prime prime in terms of the other things, right? This tells you x prime prime equals minus x prime minus x, right? And this could have been non-homogeneous. It could have involved t, but it just happened not to. So this depends on this and this. It could have also depended on this, but it just happens not to in this example. So here we know the initial x prime prime. It's negative 2 minus 1. So it seems it's negative 3. Let's give these names. So this is x, let's call this x1, or x naught, how about? Let's call this v naught, maybe, for velocity, even if x is not necessarily a position of something for this to be a velocity. Let's just refer to x prime as velocity and x prime prime as acceleration. Maybe x is something else, like a population or something, I don't know, but we can still say velocity and acceleration. So let's call this a naught equals, and then instead of explicitly writing what this is, let's just call this like f of x prime, and it could have involved t, it just happens not to, right? So this is f of x naught, v naught, and t, which is we're plugging in 0. So that's a naught. Then how do we figure out the next row here? So this is all initial data. So to step x forward by 1 unit, by this much time, I need to use the previous x prime, just like I was doing before with Euler steps. So this is just another Euler step. So what will x1 be? It'll be, so the new x is the old x plus the old velocity, or the last known value of x prime, times delta t. Right? The new x is the old x plus the approximated change in x. Rate of change times the amount of time over which the change could occur. Now here, instead of like before, before we had, in order to figure out what goes here, we had to, or let me look here. In order to figure out what goes here, we had to use the differential equation. Now, no. Since x prime is changing according to x prime prime, I can apply another kind of Euler step idea. The same way I get x1 from v naught, I can get v1 from a naught. So you see, I'm applying the same Euler step idea, but to x prime rather than to x. So shifting, doing the same thing, but shifted to the right by one column. So v1 is going to be, so the new v is the old v plus delta t times the rate of change, the last known rate of change of v, which was a naught. Then what's a1 going to be? That can be determined using these two bits of information. It'll be f of x1, v1, and the time here, which is 0.1, which is, it's delta t, that's why it's 0.1. So like that. And here I filled out another one. And here's 2 delta t, and so on. So I'm not going to show you, 3 different ways of coding this up, but for fun, I'll do it one way just to show you the result and look at the difference between what Mathematica gave when we plotted the theoretical solution, this one, and what the numerical solution gives. It'd be nice to just see a plot. Purely for fun, not necessarily to show you how to do it. I'm hoping that if you have a second order differential equation, then you can piece together the ideas here and the sort of tutorials that I showed for the first order equations, and figure out a way to do it yourself. All right, so I ended up editing this numerical code for in the Python version of things. And I threw in this annoying to type theoretical solution, and now there's x's and v's being computed here, and really I'm just showing you this to show you that I can set the time step here, delta t. So let's set it to 0.1 and then run things. Then here you see that same plot you saw in Mathematica. The blue one is the theoretical one, and the red one is the numerical one that we got by basically having it do this, and we're just plotting the x's versus the t's. So one reason I'm showing you this is so you can see that sometimes the numerical one overestimates and sometimes it underestimates. And interestingly, this one error accumulates, but eventually it becomes perfect again, right? And then error accumulates in the other direction and becomes perfect at these various times. Let's also look at what happens if I shrink the time step. So hopefully now it looks like an even better approximation. Yes, the lines are on top of each other. You cannot even see that it's 2 lines. Of course, it's not perfect, but it's pretty good. And let's make it let's make the time step really bad, like 0.5. So the overall time that it runs from is from time 0 to time 10, and the time step is 0.5. So it's like 20 steps total to do the whole thing. So that's pretty bad. And you can see it's pretty bad, right? The blue values, so they both look jagged, but the blue values are exact values where you see them, where you see the vertices here. So like here, this is for the t here, this is the exactly correct x that goes with that, but the red value is way off.